So today we're gonna do another Legion week since we did the profiler last week. So what I want to talk about today is how we manage distributed state in Legion. So there are lots of things in Legion that have to have a copy on multiple data structures. That have to have copies of itself on multiple different nodes, right? Because it's a distributed system, and so we have to have some like way of reasoning about like all the copies of certain data structures on multiple different nodes, and then how they, effectively how do we clean those up and manage the lifetimes of those objects across the distributed system. So there's a common base class for that. Pull it up. I have a couple of slides. So there's a common base class for this type, and we call this object an implementation of this distributed collectible class. So distributed collectible is going to be the base class for all kinds of different types that have to have copies on multiple different nodes. And you can see there are lots of different things that inherit from it over here on the right. All sorts of things, all sorts of data structures that some of which are user visible, some of which are internal to the runtime. But we've already talked about things like task contexts and stuff. They all are instances of this distributed collectible object. And so what we're going to look at today is the implementation of this distributed collectible object and recognize like how we keep things alive on different nodes, and then how we collect them once they're done, once their lifetime has been exhausted, and so forth. So we're going to look at that today. So the distributed collectible class lives in the garbage collection.h header file. It's probably a little bit inaptly named because it was, in fact, it is garbage collection, but all of this garbage collection is actually just going to be reference counted. So distributed collectible objects are going to be a way of reference counting things inside of Legion. In fact, Legion actually has two classes. It has a normal collectible class. So the normal collectible class is here. It's an incredibly simple thing. It's just a reference counter. So, just has a little integer references atomic here, and you can add and remove references, and when the references go to 0, the remove method will return true, saying that was the last reference, and you can actually like delete the object once you remove the last reference. But this only works inside of a single node, right? So effectively this works totally fine if you have an object that doesn't have to have copies of itself on remote nodes, and so forth. But there are lots of things in Legion, like we saw on the slide before, that don't live like that. They have copies of themselves on multiple different places, right? So like things like futures or logical regions, region tree nodes here, they all have copies of themselves on multiple nodes, and so you need to have a way of knowing when it's safe to actually collect those things, right? And so for that, we have the distributed collectible class. So the distributed collectible class is effectively just the base class. You'll see it has some pure virtual methods and stuff that users can override, or that you can override for doing specific things for different kinds of inherited classes and so forth. The main thing to recognize here is that effectively you can add and remove references to distributed collectible class with these add base GC or remove base GC and add base resource and remove base resource references. And let me explain briefly what's going on with these things, right? So effectively, the distributed collectible class has two different kinds of references, right? These GC references and these resource references. And what they're actually doing is there are two different kinds of references. They're kind of like different levels. So the GC references say that if you're holding a GC reference to a distributed collectible object on any node, that guarantees that all the other nodes, all the copies on other nodes are also guaranteed to stay alive as long as you're holding one of these kinds of GC references. If you're holding a resource reference, that is only like a local reference. That only keeps your copy on the local node alive. It doesn't guarantee that you're actually keeping copies on remote nodes alive. And so that's useful, for some cases where you need to do some stuff to clean up. But if you know that you're going to need to make a copy or send this distributed collectible to another node or something, then you actually want to hold one of these GC references. You can think of it as being globally collectible or garbage collectible, whichever you like. It's an old naming scheme. I should probably update it, but effectively these hold a reference to the object on your node, but they also guarantee that all other copies of this distributed collectible object are going to live on other nodes and not be able to be deleted either, right? And so if you actually look at there's actually like a very simple, down here, the implementation of this class. You can see they're like, in the non-debug cases, we just have atomics for counting, how many local GC references do we have inside of this distributed collectible, and we also have atomic for counting how many local resources or local references we have for keeping the object alive just locally on this node. And then there's this state object here, which effectively tracks the state of this distributed collectible object. And if we go up, the state is actually defined right up here at the top of the class here. There's a little enum state. And there's a couple states. We're going to ignore the valid ones. I'll show you where they come in. These bottom two here, we'll look at those later. But effectively, every global or every distributed collectible object starts off in this global reference state, which says like effectively, I'm globally valid, and that means that all of my copies of my distributed collectible object, are valid on all the nodes, and none of them can be collected until they all agree that they can all be collected, right, from their particular node. And so when a reference count, on any node or on a node, we'll look at the protocol for how we collect these things in just a minute. But effectively, once we've decided we want to try to collect it, then the objects will go to this pending local ref state, sort of like we're going to try to transition down to the local reference state, which says that objects can start being collected on some nodes, and only the local references will keep things around, right? And so they will try to do that, and if they fail, they'll go back to the global ref state. If they succeed, they'll go to the local ref state, at which point, like as soon as the local reference count goes to 0, then you can actually delete the object and move to the deleted ref state. So there's sort of like a monotonically decreasing state machine here, right? You start in the global ref state and you try to go down to the local ref state and then eventually to the deleted ref state once all your references go to 0. But you can only go from the global ref state to the local ref state if all of the references on all of the nodes, right, all the GC references are gone on all of the nodes for every copy of this distributed collectible object on any particular machine, right? And so effectively, the goal is to try to get to only do that, once everyone has agreed that that all of the copies of this distributed collectible are safe to be collected. And like I said, if any node anywhere is holding a GC reference, right, to this particular distributed collectible object, then you cannot transition from this global ref state to the local ref state and actually be collected. One important detail is when you actually do make that transition, you'll actually get a callback from the system to notify you that you've transitioned from the global state to the local ref state, right? And that can be useful for knowing like when the object is about to be collected, and there's some stuff that you can do, once you make that transition. But again, that transition has to happen collectively. All of the copies of this object on different nodes have to agree that things are safe to be collected. And so, if just coming back to this example to make this a little more concrete, one thing that you guys are probably familiar with are futures, right? And futures are examples of distributed collectible objects, right? And so the way to think of this is like if any like one of the things that your future handle holds that you might be holding like in a Legion application, right? They all hold GC references to the future object, right? That implements this distributed collectible class. And then that's what allows you to, pack up a future and move it to a different node and then unpack it there, is because like something is holding a GC reference, which makes sure that future stays alive, across all of the nodes, as long as that's the case, right? And then, once all the GC references have gone to 0, then we start this protocol, which we'll look at in a minute, for how to actually, determine that we can actually collect this future object and delete it once like the user has given up all of their GC references by removing all their or deleting all their handles and stuff to the future object. Okay, so let me actually before we jump into the protocol for how collections actually happen, I do want to point out one interesting thing about these distributed collectible objects, which is how do we track the names of all the different nodes that have a copy of this thing? So there's two sort of data structures in here that actually track, which nodes actually have copies of this distributed collectible object. So the first one that actually gets made is this collective mapping class. So this collective mapping class handles the case where you actually make many copies of this object on multiple nodes simultaneously, right? And so what you're actually getting, imagine a case where where we've actually got like our control replicated task or something like that, and like we do an index-based, or we do some kind of like index-based task launch with a reduction on it, so that all those shards are giving back a future, right? The runtime actually knows they can make a future object that's collective, right? There's going to be many copies of this future on different nodes, right? And so it can actually specify one of these collective mappings. And these collective mappings are just, if I actually show you what that actually looks like. I'll show you where that class is over here in Legion instances.h. So this collective mapping is a really simple thing. It's just a list of nodes, or a set of nodes that describe effectively the copies of this distributed collectible object, right? And so this is a sorted set and it names all the nodes that all the address spaces that have a copy of this particular object, right? So this collective mapping effectively just gives you a name of all the things that we knew, all the copies that we knew about when we made the instance for the first time. Now, that might not be all of the instances of that feature that ever get made, right? Or that distributed collectible. You also have this node set down here that track, effectively requests that come in, as the application is running. Sometimes you might get something that like packs up the feature and moves it to a remote node. And if a copy of that distributed collectible object didn't exist on that node before, we'll make a copy, and then we have to tell the owner node about this node set. So let me show you this picture here, which will help make this a little clearer. So when you first make a distributed collectible object, there's always at least one owner node that has a copy of the object, right? And then there might be other copies on other nodes that get made as part of making this object collectively. You don't have to have this. Some things are not made collectively. Sometimes there's only just one copy at the beginning, but sometimes you'll have like many copies at the same time that you can make one of those collective data structures, right? And there's a relationship that describes sort of a spanning tree between those things using that collective mapping. If I jump back just to make that concrete, this collective mapping class has a way to get your parent and get your children, and so effectively that's describing this relationship here between the owner node and all of these subnodes, right? So you can get your parent coming up this way, or you can get your children going down the spanning tree effectively of all the collective parts. But then you can also have copies that get made dynamically and made on remote nodes on the fly, and then they all get recorded with the owner node in that remote instances data structure to effectively know that there's like additional copies that have been made since the beginning, of this distributed collectible object on multiple nodes. And so you end up with a spanning tree, right, that kind of looks like this, right? And so the owner knows about, its children, and these guys know about their children, right? And in the collective case, and then the owner node also knows about all the dynamically created copies of this distributed collectible object in multiple different places, right? And so, effectively, if you keep you can add references, like if you add a reference to this node over here, right, that if you add a GC reference to any of these nodes, that's enough to keep all of these other copies alive at the same time, right? But if you add a resource reference, just to the owner node or any of these other ones, that will not guarantee that any of these other things stay alive, right? Effectively, you can transition down to the local only state, right? And that means that you're only guaranteed to be alive locally until your resource reference count goes to 0. Okay, so if we got back over here, so how do you actually, do collection of objects when their reference counts go to 0? So it's actually a very important thing. So let's actually take a look at,
But Mike, before that,
Yep.
You mentioned that objects may have at least one owner.
No, there's only one.
So okay.
There's always exactly one owner node. You cannot have multiple owner nodes. There's always one node that is designated as the owner of the distributed collectible object. And it is the thing that tracks, all these remote instances, right? And it also, is the root of the spanning tree with the collective parts.
So in like control replicated settings where everybody is like making the same object, you sort of distribute who are the owners of these objects you're making?
Yeah, so I mean, you don't always make them the same node that will be the owner node for like if you have multiple different features being made, right? It's not always the same node that will be the owner for all of them. We sort of round robin, the creation of the IDs, and actually that's a good transition. I should say, but like there's actually a distributed ID here that actually names this distributed collectible object, and you can actually tell what the owner node is from this distributed ID. And we generate these. This distributed ID mod the number of processes that we have today, tells you which node is the owner. So if you take this distributed ID, which uniquely references this distributed collectible object, and you mod it by the number of nodes, then you get the owner node for this particular object. So you can actually, just by having the handle for this thing, you can tell where the owner node is, which node has the actual owner object for that particular thing. And yeah, we round robin the owners in like control applicated cases, the generation of the IDs doesn't all happen from one node. So that guarantees that, you get some distribution across, who's responsible for being the owner of different objects and stuff like that. So, yep, this owner doesn't always end up being on node 0 or anything like that, which is, yeah.
How are you envisioning that scheme to work with the presence of elasticity?
So, like, effectively, you just need a different way for reasoning about the IDs. So today we sort of statically partition the space of IDs. And this is one of the things that we'll have to change, right? Like, effectively, you'll need to have a lookup table for IDs, effectively, in an elastic case, to be able to, like, determine who the owner is for various different IDs. You can't do the nice static partitioning, which both Realm and Legion are kind of relying on that today. So it will need to be fixed. We'll probably, like, it's a 64-bit address space, so you probably, like, split the space into the dynamic and the static parts, and you do the static parts as much as you can, and then the dynamic parts will have to go in the dynamic part and pay an additional cost for doing lookups and stuff like that. A 2 to the 63 address space is still pretty big. So
yeah, would it be sufficient to introduce the notion of generation for these IDs?
Not really. I actually prefer them to be so our IDs today are sort of use once and throw away. I mean, 2 to 64 is such a huge space that, like, we would in all practical cases we never run out of IDs.
Sure.
And so, like, I don't see a reason to recycle anything. We did used to recycle a very long time ago, and I suppose we could, but it makes a lot of other things more complicated, especially in the tooling system, to not be able to have distributed collectible IDs.
Yeah, I was actually talking about generation for the total number of nodes, right? So whenever there's change in the total number of nodes, then you kind of bump up the generation.
Yeah, you could effectively, like, do pool allocations, right? If you allocate a chunk for every node, and then when it runs out, then you allocate another chunk. Yeah, you could do something like that, right? Generate 1 million IDs for a particular node, but everyone has to know who owns that chunk of IDs then. So you need to have a way of broadcasting that information. So, yeah. So that'll be a tricky thing for elasticity. Yep.
How many bits are currently representing the node ID?
So like I said, like, actually I can show you where this code is. It's actually, so the way we do node ID here is actually, like I said, because we're doing it based on a modulus today, it's like all of the lower, I think right now let's see if I can actually find the code that does this. Let me copy URL here. I put it in here. I'm trying to remember, I have a couple macros that help us. We actually use the high order bits of, yeah. So, okay, so I have a couple macros that help decode these IDs, and what you can see is it's actually like the lower, what is that? All but the top 8 bits of 64. So the top 50 or the lower 56 bits of the 64-bit, ID are all used for effectively what is the unique ID. These upper 8 bits here are effectively used for encoding the type of the ID. So, like, for all of these different types here, or let's see, for all of these different types here, each one of these has a type ID that encodes the kind of this distributed ID. So, and I'll show you where that is. Over here in garbage collection.h, up here at the top, you can see we have different distributed collectible types. And so these things, are effectively what are going to be the high order bits of this particular mask over here. So those things, those high order bits go up here in these upper 8 bits, right? And that helps us know, like, when we get an ID, we kind of know what the type of that ID is. Like, is it an instance? Is it a region? Is it a future? Right? You can encode those in the upper bits. And then those lower 56 bits are all for the ID. And because of, like, how you do that ID mod, the total number of nodes gives you the owner node. You can effectively, we're kind of encoding the owner node kind of implicitly today. It's a little bit different than how, like, Realm encodes events.
So there is no static set. There's no static.
Yeah, there's no set static limit like there is in Realm on, like, this is the owner node for these things. So, But like Wan Chen said, that will have complications when you actually go to do like elasticity, where like your number of nodes might be growing or shrinking or something like that. I guess shrinking is not so bad. It's the growing part that's problematic, right? If we're losing,
So if you have like 2 nodes, then you only need like 1 bit out of those FFFs.
exactly,
to
effectively
encode
the
them.
low order bit or the lowest order bit would uniquely determine which node you're on, right? Like the one node is giving out even IDs and the other one's giving out odd IDs, right? And so, yeah,
Got it.
yeah. So
Because if there was a static, setup, and you were like 8-bit or however many
Right.
bits go to node ID, then
you'd be
elasticity-
wasting. You'd be wasting in
Right,
that
you
case,
would be
right?
wasting,
But
yeah.
in this case, we're not wasting, which is good, but also a little bit more like restricted to the fact that there has to be a fixed number of node IDs or fixed number of nodes, and if it grows, then we have a problem, right? So, yep. And this is up here in the top of garbage collection.h, and so you can see these are the type encodings for all of the different kinds of things that can be a distributed collectible, and so those go in those upper 8most bits of the ID to help us like identify, like if you get a random distributed ID, you can tell what kind of type it is, or what kind of object it is just from that. And you can see there's lots of different things that sit on top of this distributed collectible class. Let me actually, before we go into the collection algorithm to actually show you how we actually collect stuff, I do want to give just a little example of how this actually works in practice. There's actually a tool that you can use to actually look at all the references and all the distributed collectible objects that actually get created in a Legion application. So if you add this flag, Legion GC, to your compilation, hopefully this compilation will be relatively, need to set the path here. Hopefully my cache will be nice and fast here for compiling this. But effectively what this will do is this will actually log for us all of the references that get added and removed to distributed collectible objects and all their different kinds of references, and it'll even capture nested references. And so if I actually run this code and I pass in, I'm going to do some logging on this Legion GC logger and make a Legion GC log file. And it runs. And then I can actually use this tool, legiongc.py, and this will actually tell us, I'm going to pass in the L for looking for leaks. So it's effectively going to check for any leaks of any of the distributed collectible objects. Are there any that were still alive when the application exited, right? And V for verbose to dump out detailed information about all of the references and so forth. And so what this does is it actually like checks for leaks on all distributed collectible objects. So when you look at these things, like here's a leaf context object. Its distributed ID was 51. We only had one node in this run. This is on my local laptop. And you can see effectively, there were no empty or no refs left at the end. This thing was properly deleted. It had one base GC reference added with its provenance coming from the single task reference and one removed. I can scroll up, I can see all sorts of other kinds of distributed collectible objects in here. Here's a region, right? Here's some index space expressions. I've got more index space expressions. Up here at the top, I've got other stuff. I've got index spaces, some of which have lots of different kinds of node references. So you can see there's both like GC references as well as resource references being added and removed. In some cases, I can even see like nested references. So that's actually like, this index space was also being referenced by another distributed collectible object, like this part, or like by this materialized view here, right? Had a nested GC reference from this materialized view, right? Which got added and removed and so forth. And so this is actually really useful for finding like leaks in your reference counting scheme, right? Because there's actually lots of cyclic references between these different distributed collectible objects. They can often point to each other. And just to tie that back to the code, let me actually show you where those, I come back here to this, to where we're adding and removing references. You notice there's two different method calls here. There's the add base GC reference and add nested GC reference. You'll notice this base GC reference just takes a reference source, which is just an enum up here of different provenances for different kinds of like where you're acquiring a reference from some other place. And this is very useful for like giving you some indication of who added a reference to this distributed collectible object in the cases where you want to find, like a leaking reference or something like that. But you can also add nested references, right? And so this is where you're actually adding a reference from another distributed collectible object, right? And so you can actually pass in a distributed ID, right, from another distributed collectible object, and that will actually tell you effectively, that another distributed collectible object added a reference to this distributed collectible object, right? And so in this report here, that shows up as these like nested GC references where like some other, object like this materialized view here added a reference to this, index space distributed collectible object, right? And so you can actually like see those kinds of relationships. And Legion GC also has a cycle check to make sure that there's no cyclic references here in any of these objects, right? And so you can actually, if there have been cases where, I've accidentally created a scheme where I've added references in a way that actually creates a cycle in these object graphs, which, obviously we can't collect. There's no garbage collector here. Everything is reference counted, so there better not be any cycles. So you can use Legion GC for checking that as well. So that's a useful thing to do, is to, like, if you know you're adding a reference from one distributed collectible object to another, use the nested version instead of the base one, which just gives you sort of like an enum provenance. So this one is actually much more descriptive. But if you're not adding, then just adding one of these is fine. And if you need to add like a new provenance kind that you want to track, just go ahead and add it in here into this reference resource kind of enum here. And then also update this list of strings that give you the nice, sort of string representation of what all of these different things are. At some point, I will macroize this and make it a nice, couple these two things together. But for the moment, they're kind of separate from each other. And these strings are what get printed out by Legion GC in these reports over here to show you all these reference counting things. One nice thing that I'll also point out here is that you can see these node annotations, right? So you can see like, here's a nested GC reference from this partition on node 0 onto this region on node 0. In cases where you have, multi-node runs, you'll actually get references, that will actually come across nodes, right? So you might have a reference, added from another node, from distributed collectible on another node. And so you'll actually get to see that kind of information in your distribute settings here in these kinds of reports as well. So Legion GC is a useful tool for you to use, like for checking your reference counting scheme and making sure that you're actually like adding and removing references wherever you want, or adding and removing references correctly and not leaking anything, and also not creating any cycles that cause things to live forever. Okay, one other macro I'll mention since I'm on the debugging track is that if I actually scroll down here, we also have this debug Legion GC thing, which will actually use that provenance information for something else. So if you pass in, like, if you're adding a reference from another distributed collectible or from a reference source, it'll actually check that your adds and removes will actually match up, based on those provenances, right? So, in the normal case, we're just tracking, the total count of GC and resource references. But, it's actually important that, like, if you added a reference from one distributed collectible to another, you actually remove that same one, and you don't remove it a different way, like with a base GC remove or something like that, right? And so if you enable this debug Legion GC macro, it actually, check that you're adding and removing references with the same provenances and not messing anything up. So that's another useful debugging macro in there, which will help you, like, check if you're adding a reference of one kind and then removing a different kind and not matching up your adds and removes correctly. But that's off by default. Both these things are off by default because they're kind of expensive to use, but you can turn them on in your build to check for that your reference counting is being done correctly in different ways. Okay, so let's actually take a look at what we actually how we actually know that it's safe to do the collection of a distributed collectible object. What is the protocol for actually doing this? So let's actually look at remove base GC reference here. Okay, so here's the inline. This first implementation of this inline method is actually this inline method. Effectively, this remove base GC ref in many cases is actually a very cheap operation to do. There's a lot of macros here for various different things. Checking that your count is positive. Probably should just make that unsigned integer. Here's some logging for Legion GC. This is the special case, for debug Legion GC. It'll actually go in and do everything with the lock to make sure that it's checking those data structures correctly. But this is the common case down here, this else branch. This is the common case. And what you'll see is there's actually a little shortcut here. We want to make reference counting really fast in the common case, right? And so in most cases, we don't even take the lock to update the reference counts, right? So effectively what we're doing here is, we're doing an atomic load here on the GC reference count. We're getting the current count. And, it better be bigger than or equal to the current count, right? Because if it's not, then we really messed up and we don't have we're effectively trying to remove more references than exist, and that's usually a very bad thing. Right, but in the case where current is actually, the current count of references is greater than the count that we're removing, right, we can actually try to do, effectively try to remove this without even taking the lock, right, and going into the actual object itself and actually doing the more expensive collection, right? So effectively we have a fast path here, right, which effectively, looks at this and tries to do, we compute what the new count should be, and then we try to do a weak compare and exchange to actually try and update that count without having to actually even take the lock, right? And most cases, this will be true, and this compare and exchange weak will pass and will return false because we're not ready to collect this object, right? It's not deletable yet, right? And so effectively, this should be the most common case. In fact, nearly all references do the same thing. And there's similar paths for the add methods and stuff too. You can come look at those. They're up here right above this, right? They effectively have fast paths for if we're not the first reference to be added, right, then we can just do an atomic update. Otherwise, we have to go actually do and do the update, the adding the GC reference ourselves, right? But that should be the common case. Now, in the case where that's not the case, we actually are going to go into the object, call this member method, and actually take the lock and try to do something more expensive. So let's actually go look at that remove GC reference passing an account. And you'll notice that effectively all the provenance stuff, like this reference source and this distribution ID source, right, they all go away by the end of this method, right? So then we're calling this in both cases where I actually end up in this, remove GC reference common case or non-common case here, right? All the information about the provenance stuff is all logged and stuff as part of these initial method calls, and they don't actually go through. Effectively, we do all that provenance checking on the front end here. Okay, so let's actually go look at remove GC reference here. Okay, so this is the non-debug Legion GC case, right? So watch your macros in here. There's lots of, in some cases, there are different implementations of these methods depending on whether we're in a macroized case or not. But this is the right one to be looking at. So you notice in this one, this is the case where we now need to take the lock, right? And we better be, if we're removing a reference, we better still be in the global collectible state, right? Effectively, we can't collect anything until all of the different objects have agreed that the GC reference count is 0. Right, and effectively, we're going to now be able, because we've got the lock, we can actually do something. We actually know that it's safe to actually, do this update, directly without having to do the compare and swap. So we can actually remove our count, right? And if the count has now gone to 0 on this particular node, right? This is all happening on one of these nodes in the system. Just to refresh, you're in one of these nodes, right? But you don't know anything about any of the other nodes yet. So we're still sort of imagine we're removing a GC reference from this node here, right? So we're just doing our local, sort of reasoning here, and kind of ignoring the rest of the global collective or global state of the other objects and other copies on other nodes, right? And so, effectively, if our reference count, fetch sub, this returns the count before we did the fetch, right? And so if they're equal, then we now know that our reference count has gone to 0. And then we're going to try and actually to see if we can actually delete this distributed collectible object. If it hasn't gone to 0, somebody else came in and added a reference, then we're done, right? We don't have to do any work, right? We can return false, say this is not ready to be collected, and we're done. So let's go look at can delete. Okay, so can delete, right? We look at our current state. Let's ignore the valid stuff again. I'll explain that hopefully by the end of the meeting. But let's imagine we should be in one of these 3 states, or I guess we can get called into here from many different states. So we can either be in one of our global states, right? Effectively, either we're global or pending local ref states, right? Those are kind of the two that we've talked about so far, right? Either we're currently global, or we'll see where this pending local ref state comes in. But that means that we're still global if we're in the pending local. It means we haven't actually made it to local yet. We're still in the like, can we transition state? In these cases, right? Actually, before I go into these cases, let me just explain the local ref state. In the local ref state, that means that like we've already agreed that all of the the nodes are kind of on their own at this point. We've run out of GC references across all the nodes. They've all downgraded to the next state, to the local ref state, sort of cooperatively, and that means that the only thing that matters are the resource references. And if your resource references have gone to 0, then you can move to the deleted ref state and you return true. That's the very base case. But let's say we're in the global ref state, which is the state that most likely we are going to be in, right? Effectively, there's still global copies. There's still GC references at least somewhere in the system, as far as we know, and we want to try and see if we can collectively do a downgrade, right? So the first thing that we check is can we downgrade? So can downgrade is a pretty simple method, right? In the distributed collectible case, right? Effectively, it's just checking to see like are we better be in one of these two states, either global ref state or the pending local ref state, and have our GC references count gone to 0? If so, like then we know we can try to downgrade on this local node, right? Because effectively our local GC references have gone to 0. So pop back to can delete, if I can type. So let's say that we have, in this case, our GC references have gone to 0. The next thing to do is determine if we are this node, which is called the downgrade owner. So let me explain what this is. So if I come back here to the header file, we're in the distributed collectible object here. Every distributed collectible object has one downgrade owner. And the idea is that there's one node in this collection of all the copies of a distributed collectible object, which is designated as the node who is responsible for initiating an attempt to perform a downgrade, right, from one state to the next. So somebody has to decide that, let's start the protocol to actually do this downgrading. Now, the initial downgrade owner is always the same as the owner node for this spanning tree, right? It'll always start here because that's a pretty common, obvious first case, right? But as you're going to see, this protocol, that downgrade owner might move around, right? So effectively, what might happen is like maybe like the downgrade owner starts here, right? We remove our GC reference here from this owner node. It starts the protocol, and I'll explain what the protocol is in a minute. Let's just assume it runs the protocol to try and see if there's a GC reference anywhere on any of these nodes. And it finds one. Let's say it finds one on like this node over here, this collective node over here. There's still a GC reference over here. Well, then we will make this the new downgrade owner because it still has a reference. And so, effectively, as soon as its reference count goes to 0, it will know that it's the downgrade owner, and then it will start the process of trying to do the collection, right? And so maybe it'll run the protocol again across all the nodes, and see if any of them have a GC reference, and maybe it finds some other node over here. Maybe this copy over here has a GC reference still. Well, then this will become the new downgrade owner, right? And the idea is that the downgrade owner is the one that will ultimately make the decision, like, is it safe to perform the downgrade? And if not, it will assign a new downgrade owner to something else that still has a GC reference, right? And of course, if it can't find anything that still has a GC reference, then then effectively it can broadcast out to all of these guys like, hey, you can all transition from the global state down to the local state only, right? And at that point, they're kind of on their own for deleting themselves, right? But effectively, the downgrade owner will move around depending on where GC references exist in the copy of all of each distributed collectible object, right? And so if we come back to the code here, jumping back over here, effectively, if we're not the downgrade owner, there's nothing for us to do, right? Because we're not the one responsible for initiating the protocol to try and collect this object. Somebody else somewhere is the downgrade owner. They probably still have a GC reference, and they haven't bothered to like try and perform the protocol to actually, to see if it's safe to actually delete the distributed collectible object. So we can return false and say you can't collect this thing yet, and we're done, right? It's a very simple path, right? Now, if we are the downgrade owner, let's say we are like we've been assigned to check to see if we should do the downgrade once our GC reference count goes to 0. Okay, so we're the owner, our reference count has gone to 0. Let's start the protocol to actually see if it's safe to collect all of these, or to downgrade all of these objects, from our global reference state to the local reference state, right? So effectively, there are a couple of different cases here. Effectively checking to see, like, this big if condition here, right, is really checking to see, are there any, like, should we start the protocol to actually, or do we have messages to send to other copies of ourself, right? So either if we're not the owner, then there's definitely other copies. If we're the owner but we have remote instances, there's definitely other copies to talk to, right? If we're the owner and we've got a collective mapping, right, there's definitely other copies to talk to, right? And so in those cases, we're actually going to do this check for the downgrade, right? And we'll actually go look at that. In the case where there are no messages to send, well, then we can immediately, go right to the perform downgrade. Like, let's say that, there was only an owner node, there were no copies on other nodes and stuff like that. You can immediately just jump and perform the downgrade. But in the distributed case, most likely you're going to be in this, like, check for downgrade path. Now, let's actually take a look at that check for downgrade. There's a little check here to see if, we're still in our safe to downgrade mode here. But I'm going to explain, without actually walking through all this code, I'm going to describe what the protocol is doing, so you guys have some sense of it, because the code is actually, there are lots of cases for this, for where, depending on whether you start, whether your downgrade owner is on a remote node or a collective node or the owner node, there's lots of different cases for how to do this protocol, but the protocol is all the same. And what the protocol does is, effectively, let's say our downgrade owner is this collective here. Okay, so his reference count has now gone to 0, and he wants to do a search to see if all the other copies of this distributed collectible still have a GC reference or not. So what it does is effectively says, okay, broadcast out to all the other copies of this distributed collectible to see if they all have a GC reference, right? And effectively what it does is it puts, in order to do that, it actually does a two-phase protocol. So what it does is it sends out this message saying, I'm trying to do a collection. Tell me if you're if you still have a GC reference or not. And if not, go into this pending local reference state. So it sends messages to its children. It sends messages to its parent, right? And its parent will broadcast out, like, to the remote nodes as well as down this side of the tree, and sends this message to everyone. And everyone then checks their state and says, if I have a GC reference, I return that, like, I still have a GC reference. And by the way, this is my name of my node that's still, like, I still have a GC reference over here. Eventually that will propagate in messages back along here, back to this guy, right? And say, like, this copy here still has, at least one GC reference. And maybe he gets multiple, messages back saying there's a GC reference here and a GC reference here. He'll pick one of this owner node will then pick one of these guys to become the new downgrade owner, right? I think we have some really simple protocol, like the smallest node ID, becomes the new downgrade owner or something like that. You just have to pick one. Doesn't matter which one you pick, but you pick one of those guys to effectively say, you become the new downgrade owner. But if nobody responds, they still have a GC reference. All of these nodes are then in this pending local reference state. So, like, one tricky part of this, if I come back over here, right? Let me just show you the state machine here, right? So effectively, if all of the nodes actually have gone to this, like if they've all acknowledged that they've seen the notification to try and do the downgrade, right? They all will go into this pending local ref state, right? And the reason to do that is that, right, that all these guys are now in a pending local ref state, and this distributed collectible object has seen a response saying, like, hey, we've successfully, notified you that there's no GC references. But there's actually two cases that you have to worry about, that you can't actually just move them directly to the local reference count case. The owner node, the downgrade owner, has to check two additional things before that happens, right? There are two kinds of races that can occur where, like, things might still be in flight at the same time that we're trying to do this downgrade. So the first case, right, is that a reference, like, may have been, for one of these objects, may have been packed up and removed from, like, one node, and might still be in a message in flight, between two nodes, in the process where we're actually trying to do this downgrade response or downgrade protocol, right, to try and change states, right? So there might still be a reference that's been, that's packed up in flight in a message, right? And so there's a very clever way that we try to actually deal with that problem. So we have these methods here that effectively pack and unpack. Actually, let me actually explain the other one. I think it might actually be simpler to understand. So let's see. Let me actually find the right method here. Where is check? Let's see. Where did it go? Check global and increment. There we go. So one thing that can happen, right, is while we're actually doing this protocol, like this node is trying to do the downgrade, there are these methods here, check global and increment, which allow you to effectively check this. These are effectively atomic check and increment operations, right? So effectively check to see, has this distributed collectible been collected or downgraded to the local only state? And if not, add an increment. And you can do this on any node in this system, right? So like there's a few cases for this check global and increment, which effectively says like, check to see if like maybe this copy, maybe I do a check global and increment on this copy, and at the same time there's a protocol trying to do a downgrade happening in progress, right? So the check global and increment is really simple, right? Effectively, it will actually say like, am I in the global reference state? Like if this node is still in the global reference state, you can immediately say, okay, we're still global and we can increment the reference count on this object. However, in order to avoid races with the downgrade, process, right? Effectively, if we detect that this node is in a pending local state, we then have to send a message to the downgrade owner, right, to try and race with the downgrade protocol, right? And what that allows is that like, this downgrade owner here, whether he sees responses from all the nodes, saying they've all done their update to pending local and they all didn't have a GC reference, right? Then if that happens first before this like check global and increment arrives here, right? Then the downgrade will win the race, right? But if the check global and increment object, detects there's a local state or pending local state here, it will send the message, eventually to the downgrade owner. It kind of does a search through the tree to find the downgrade owner, right? If that message gets here before this downgrade owner gets the responses from all the other copies, right, then that will effectively say, oops, we're gonna the protocol will fail, right? We won't be able to do the downgrade because we got to check global and increment, that got here first, and actually ended up beating us out, right? And so that's one way that you can kind of defeat the protocol for downgrading is if you get one of those check global and increments, right? And there are some useful cases that we'll actually probably see as we're doing later talks and stuff of atomically doing this check and increment on some of these objects. So that's one way that you can defeat the downgrade protocol. And like I said, the other way that you can defeat it, right, is the case where a reference might have been packed in a message, like serialized in a message that's still in flight, and obviously the downgrade protocol can't see. It can only see references that exist on these objects themselves, right? It can't see things that are serialized in messages being moved from like one node to another, right? So like, maybe a reference was packed up in a message from one node and it's being sent, over here. So this message is still in flight. In the meantime, the downgrade protocol is sending its own messages, which might race past, right, some of these things and then get sent back, right? Before this message, that was in flight from one node to another actually ends up being delivered, right? And so if that's the case, you need a way to detect that as well, right? And so there's the way that we actually treat or detect that case, right, is we actually have these methods. You can pack references into a message, and then you can unpack them on the remote side. We have these methods here that actually help you with that. And the way that we detect this is that every one of the copies of the distributed collectible object here, right, effectively track how many sent and received kinds of references they have packed, right? They track, their sent, like if they pack a global reference, they increment this sent global references count, and if they've received a global reference, then they unpack, then they increment this counter over here, right? So these are monotonically increasing counts, and every time that you pack, reference, you increment this count. Every time you receive one, you increment this count. Right, and so if you're sending a reference from this node to this node, and you want to make sure that reference is still held while it's in transit across those nodes, you pack the reference on this node, which will increment the sent count on this node, right? And then when you receive the message over here, you'll increment the received message on this node. And so when you do this protocol for doing like the collection, right? If the downgrade owner is trying to actually do the collection for all these things, right? What it actually does as part of the protocol for doing the like update, like check to see if there are any GC references, it also aggregates a sum of all the sent and received counts across all the copies of the distributed collectible object, right? And what that means is that effectively, like if you sum up all the sent messages across all the copies and you sum up the received messages across all of the copies, right? If they're equal, then you know that there are no messages in flight between any pair of nodes inside of this system, right? Like effectively, there's no packed references still in transit in any messages anywhere inside of the system, right? But if your counts don't match, right? If there's more sent or packed sent references than there are received sent messages, then even if you detect that there are no GC references on any of these objects, right, and no global check global and acquire races or anything like that, if you still can detect that there are still messages or references that are packed in messages, right, then you still cannot do the downgrade, and you have to wait to see, where the unpacked reference shows up. And wherever that unpacked reference shows up will end up becoming the new downgrade owner once it actually does. There's a little bit of like a polling process in that case where like the downgrade owner will keep trying to downgrade until it detects that there's a GC reference somewhere added, by one of those messages that eventually arrives and unpacks itself. In order to avoid like live lock conditions, we actually will the messages for this downgrade protocol are actually put with very low priority, and that tends to allow messages like that have packed references in flight to actually be able to arrive and add their references before, and not be starved out by like this downgrade protocol, sending messages everywhere to try and do the downgrade all the time and starve out the messages that actually are carrying references and so forth like that. Okay.
Can I ask a question?
Yeah.
Like in normal operation, you're saying like this race.
Yep.
Happens before, let's say that the owner node is making the middle remote node is sending the global reference there.
Yeah.
Right?
Yep.
When would the link be established? It sounds like the way you're describing it, it sounds like first we send the remote reference, and at some point when it's received, this link is established between the owner and the remote. So you're describing, right? You're describing a case where the link has not been established, but would be if you waited for a few more seconds.
Exactly.
Right?
Yeah. Like effectively the message, like, so the common case is like maybe this owner had a GC reference, right? But like maybe the GC reference is transitioning to another node. Like we're sending a message to this remote node who's going to become the new thing that's going to hold the GC reference, right? So we know that we're going to remove the GC reference on this owner as soon as we pack up the message and send it, right? So like we need something that keeps a reference to the distributed collectible object while that message is in flight, because we know the owner node is about to lose its GC reference, right? Like we don't want to have to like wait for a message send and then an acknowledgement to say like, hey, it's safe to remove the GC reference on the owner. That's actually expensive. It adds a whole nother message into this round trip protocol, right? Like effectively you'd have to like hold the GC reference here until you sent the message, added the new GC reference up here, and then sent a response message back down here, right? To then say it's okay, safe to remove your GC reference, right, on the owner node, right? And so in order to avoid that, right, you can pack up one of these GC references and then send the message. The message is in flight. You can immediately remove the GC reference here on the owner node, right? And that allows you to effectively, get rid of that reference, right? There's still a reference in flight here, right, which the protocol can't see. It's packed in a message, right? And so like we're still technically holding the reference, but the message is in flight. It's not visible to the protocol because, right, it's not actually living on any of the nodes at the moment. But once that message eventually gets here, it'll unpack that reference and then add a proper GC reference on this remote node, right? And then you don't have to send an acknowledgement message, right? Like effectively you just kept that in flight, right? But the protocol, will be able to detect that message was still in flight at the same time that you're actually sending the reference, right?
So the idea is that there's no acknowledgement, so the owner knows about like the new remote.
It does.
So the issue is that let's say you race with the downgrade. So the owner will still send. Let's say that the downgrade reaches the remote before the creation. Like that's the race, right?
Yeah.
So in that case, the remote will be like, what is this distributed collectible? I have no idea.
Oh, so yeah,
right?
you're
Is
even.
that what you're describing?
No, so I was actually talking about the case where the remote already exists, but you're right. There is a case here where the remote like doesn't even exist yet, and so like in that case, the downgrade, sort of message that gets here even before this remote object is created, like we know the owner has sent, a message to create the copy on this node, right? In that case, the downgrade, response actually knows how to defer itself and wait for like the creation of this this copy over here.
Mm-hmm.
So yeah, there is a race in that case too, where like effectively if this object hasn't even been created yet, but the owner knows that it sent the message to do the creation, right? Then like the protocol could have sent a message here, which then sends a message to this node to say like, hey, please check for downgrade on this thing, and it doesn't even exist yet, right? We know to defer ourselves in that case, right? We know that that like the message will eventually get there and create the thing for us.
Okay, so you're describing the case where the distributed collectible exists, but there's an incoming increment.
Increment. That's right. Yeah. Yep. Yeah. There's definitely the race that you're describing as well of like the object doesn't exist yet. It hasn't been made yet. Right. We sent the message to create it, but it's not there yet. Right. And we handle that case, but that one's actually simpler than the case where like the reference is still in flight, like the updated reference.
Okay.
Yep.
Yeah. I guess I was like, well, why didn't we acknowledge? But you you solved that. You answered that.
Yeah. And like the thing that we're optimizing here for is, right, we don't want to be sending acknowledges and having to do like back and forth to like, every time you pass a reference from one node to another, you don't want to be sending in both directions, right? And so this optimizes for the common case where like, effectively we're not actually collecting all these things very often, right? Like distributed collectibles don't get collected that frequently, right? And so we don't, but they do move around and they do move references quite often. And so like we want to make the protocol is sort of geared towards the case where, collection is a little more expensive, but much more rare, right? And moving references is much more common, and adding and removing references on different places needs to be fast. And in particular, adding references locally should always be very fast, right? Like so adding a GC reference, is pretty much always fast, or doing a check global and increment is almost always fast because you're almost hardly ever in that like in the collection state where like this protocol is trying to do the collection and so forth. But the protocol is still correct and deals with races and so forth. Okay, we're at time, so I want to take just 2 minutes to mention a couple of other edge cases, which we'll probably cover in future lectures. But I did sort of tease you guys a little bit that there's this there are these valid reference states. So there's also a distributed collectible object which has another set of states called the valid distributed collectible class. And so what this one does is effectively just adds a new kind of state called a valid state, which is like another state in this protocol, right? So effectively, in this case, you actually have to do 2 downgrades to delete a valid distributed collectible. You start in the valid reference state, then you can go to like the pending global ref state, and if your downgrade succeeds, you end up in the global ref state, and then you can do another downgrade going down to the local reference state. And as you might expect, right, the valid distributed collectible has some additional methods for adding and removing another kind of reference called valid references. So this gives you sort of like a double downgrade. You can have an additional state that you have to downgrade through and a new kind of reference that you can add to this thing. And you'll see that like in the type hierarchy here, right, there's only really one thing that implements the valid distributed collectibles right now, and that are these index space or index tree nodes, which are index spaces and index partitions. And so we'll probably see some examples where we use these valid references to handle, like why we have 2 different kinds of references to keep track of global stuff, both the valid and the global ones. So we'll look at that, but just be aware that there are these things called valid distributed collectibles. And the one other edge case that I will mention here, which we won't get into today, but just want you to be aware of, is that in the case of the instance manager, the instance manager also has a valid state. And so let's see. Am I in the right header file? Nope. Here we go. So in the physical manager state, it also has a concept of adding and removing valid references, and it has its own little valid distributed state. The difference between the valid state with the physical managers and the valid state with like the valid distributed collectible is that in the valid distributed collectible case, right, we just do downgrades. These states are monotonic, right? So once you go from the valid reference state down to the global reference state, you can never go back to the valid reference state, right? Like we move sort of down, we move down this chain, right, from valid to global to local, and you can never go back, right? The difference with instances is that the valid state is actually a function of like the acquires and releases that applications do. And so like in the physical manager case, your valid state can actually transition back and forth between valid and global and bounce back and forth, as references are added and removed. And that sort of determines whether this object is actually eligible for collection. And so there's a slightly more complicated protocol for the physical managers for doing garbage collection and knowing when it's safe to do like a collection of a physical manager, like detecting in this case, like, are there any valid references to any of these things, right? And knowing that your states can jump between valid and global back and forth makes things a little more complicated. So that will be a case for another day. But an instance is still an instance of the distributed collectible class for the global to local transition, right? And those are still monotonic states, right? Moving from global to local. So that will be a discussion for a future day. But just like when you do manage these distributed collectible objects in Legion, right? Just make sure to think about like, adding references and making sure you're adding and packing and unpacking references in the right places and stuff to make sure that you're keeping things alive wherever you need them to be and adding the right kind of reference, whether it's a GC reference to keep everything alive on all the nodes because you might need it on a different node at some point in the future, or whether it's a local reference, right, that just needs to keep the object alive on this particular node until it's safe to delete. So, yep. Okay, that is distributed collectible objects. Next week, we'll be back to talking about Realm. Unless I'm happy to take any questions here at the end before we stop the recording, but otherwise, I think we'll call it quits for today. No questions? All right, we'll see everybody next week.